Let us consider the case when a single power supply is used. This transfer characteristic is different because of the single supply. It is not centered around the origin, and you can see that both the voltage limits are in the positive half. However, it is also nonlinear. Our task is to achieve linear amplification. But how to do that in a nonlinear transfer characteristic? The technique is to bias the circuit to operate at a point near the middle of the transfer characteristic. That way, maximum output swing in both directions would be possible. We apply a DC voltage Vi as indicated in this figure. The operating point is labeled Q, and the corresponding DC voltage at the output is V0. This point Q is known as the quiescent point, DC bias point, or operating point. The time varying signal VIT to be amplified is superimposed upon the DC voltage Vi as shown here. The instantaneous input Vi, that is any point on this graph, is given by this formula and varies around capital V subscript capital I. That is the Q point. Tracing it here, we can determine the waveform of the total instantaneous voltage V0. If VIT is sufficiently small, then we see that the output does not get clipped nor distorted. It doesn't get distorted because a small VIT ensures that the instantaneous operating point with coordinates small v subscript capital O and small v subscript capital I are confined to an almost linear segment seen here. This ensures linearity and hence no nonlinear distortion occurs. The instantaneous output is given by this equation over here, with VOT, the unbiased signal output, given by, with V0T, the unbiased signal output, given by this equation, where AV is the slope of the almost linear segment of the transfer characteristic, given by dV0 over dVi at Q. So again, if we confine our signal to this portion of the graph, we can achieve linear amplification. The price is that the input signal needs to be kept sufficiently small. This is because we don't want the output to cross these limits. This technique will be used when we formally study transistor amplifiers in later modules. You might have been overwhelmed by the different symbols that we used in this video. So here's a little primer on the symbol convention that we are going to be using in this module and the rest of the course. This value read as capital V subscript capital O is the DC value. This one to the right is small v subscript small o, and this is the small signal AC value. The leftmost one on your screen is the instantaneous value, and it is denoted by small v subscript capital O. The relationship between each of these values is given by the instantaneous value is equal to the sum of the DC value and the small signal. Now, what does the small signal look like? Let us take an arbitrary signal, a sine wave. Now, what happens when we add a DC value to it? Or in other words, we superimpose the small signal onto the DC value. You can see on your screen that the small signal is shifted upwards by the DC value. So what is the instantaneous value? Any point on this graph is the instantaneous value of the voltage. It is always a sum of the DC value and the small signal value. Hope this part is now clear.